I will talk about the Tiresias system we developed within Semantic together with UCL and Boston University to predict the security events. First thing first, this is a teamwork. So you have Enrico and Gianluca on the first row. They are on site. Pierre is not. So feel free to grab them for the following up questions. This is actually the outline of the talk. I will talk about our motivation at the beginning. Then we talk about our challenges when we try to resolve the issues coming up and design of the Tiresias systems. I will talk more about the limitations and discussions because we want to be open so we can actually have open conversation over the limitations. Then I will conclude that talk. So for the motivation, we have done a lot of detecting attack research for the past decades. There are rich literature available. But recently, we see the trend that we can leverage our detection technologies to start predicting the malicious events. For example, starting from 2014, hope this list is exhaustive enough, we have seen quite a few very successful papers on predicting different things. For example, the website would be compromised or data breach gonna happen. And also the paper from our company is about the host would be getting infected by malware by Layla last year. And all sorts of these prediction efforts there. One thing that we want to further advance the approaches is because the previous approaches require feature engineering. So normally they will connect the data, extract predefined set of features in that period, and they need a reasonable amount of label data to build the prediction model. And they will provide you the binary prediction. So yes or no, your system gonna be breached. So that's the summary of previous models. So for us, we started asking ourselves the question, what if there's an approach? Not just give you an indicator that your system will be breached or not. We can actually offer you the exact security attacks you may actually face by an adversary, or predictable by what the user gonna take. For that, if we're able to realize this dream, I would say, it opens doors to different things because we actually can be a step ahead of the adversaries. For example, we will be able to deploy the proactive measures or countermeasures based on the things we predict on the condition that the prediction with high confidence. And suppose that you have a SOC environment, then you have the overview of all the systems you can predict. Then you will see the scale of the attack within the next time step. All sorts of the things. But of course, a couple examples will be better to illustrate how the things can benefit the security research. So for example, this one, we take the intrusion prevention system. We will be able to see the different multiple steps attack is happening in the system. We can see that started with the default credential login, then just keep on going, trying different ways. If we were to be able to predict, you can see that hollow square there. If we can predict the next thing they're gonna try is using a known CVE vulnerability, you can ask yourself the question that, is this system actually properly patched? And how many machines that has been patched? How many machines have not been patched? And all sorts of the scales you can see from your system. Another interesting application, you can see that if you solve the problem, you will be able to predict what the user gonna do in a cloud environment. So for example, this one, you can see it started with describing, there's an alarm raised. Then the user just keep on going and saying that describe the trails and all sorts of the Bitbucket location. And finally, this is actually a real world example. It is they have the scalability issue, so they decided to create a VPC. If you have the prediction, you will be able to proactively understand what would be the best solution to deploy your new VPC cost-effective way in a region, and actually can you actually apply your best practice per region. all sorts of the things. But what is the challenge? The challenge, first thing that we face is the concurrency from the different parties. So if you take this IPSP system, for example, you will be able to see that if there is an attack, the attacker actually unleash this attack to this system. At the same time, it will actually see all the activities from the different users and also the different attackers. So from the top, you will be able to see that that is the multiple step attack we understand. And at the telemetry level, we connect it, will be see the noise. For example, the first one is E4, but there is a noise event, the E27. Then you will see the rest of the tag lined up. So that's the first challenge. The second challenge is keeping track of the tags across different machines and time as well. That will be how moving from the one dimension, you will actually have the second dimension is the machines. So you have that tag to the different machines, and different machines will show the different noise level, and the same attack will be buried in the noise. So the motivation is, if we were able to detect, we actually learn a sequence prediction function. So I have to go abstract a little bit. To learn a function prediction f, that will take the variable length of the security events or the user behavior data to predict the upcoming event. So that is our problem here, and we want to solve it. This actually leads us to the Tiresias architecture, which is pretty straightforward, and we will actually explain a little bit more on this, even if it looks quite simple from the architecture perspective. What we do here is to have the adversaries. They will actually attack the different system. They will actually record the sequence data. So we pump into the data processing module. We can reconstruct the sequences from different machines, and we'll go through both the training and the validation step to build our prediction engine. But of course, how do we build the prediction engine? It will be built using our recurrent neural network system. So first, for example, if you see the same example from the IPSP sequence, what will really happen at the sequential level if you can actually replay it back? First, you will see E4. Then after that, you will see E10. So you have the relationship that if you see the E4, you will see E10 after this. And the second timestamp, you will see that E4 and E10 happened, and you will see the E11 after these two, and so on and so forth. What we do is to build this recurrent neural network, because this is actually a quite nice natural fit for the recurrent neural network, especially the technology we use, the recurrent memory cell, to build this sequential relationship and predict basically train and predict the next event. If we dive a little bit into the model itself, we use the recurrent memory array. So originally we tried to use the multi-layer recurrent neural network architecture. The problem is that we have billions of events, and the sequences actually make the system incapable to do the computation. So we found this nice solution which uses the stochastic output pooling, which will actually train a different memory cell in the single LSTM cell itself and output at a different level based on the input sequences. So that's the Mars part. We don't want to save too much on it. So we have the model, we have the challenge. The real question is that, does it work in a real environment? So we connected 27 days of telemetry data. We divide into two, D1 and D2, you can see in the figure. We try to be as random as possible to select the different days to test our system. I will cover about how we set up the evaluation. And for both data set, it reaches 1.2 billion events. But the real challenge is that for the IPSP system we use, the data set we connected has almost 45 4500 unique events. So for our prediction problem, it will be choose one out of 4500. That's the real challenge there. To set up the evaluation, we strictly request the training, validation, and test data coming from different machines. So we don't reuse any machine to test our system. We follow the 80% for training, 10 for validation, and 10 for test. Since our system gonna be modeled as a multi-class classification problem, we use a micro-precision metric to evaluate it. So there are actually 4 questions we want to answer. The first 2 questions is that, does Tiresias work? And why it works? And the second 2 questions is about, can we actually reuse the model? And if the model is stable enough. So these are the main questions we try to answer at the evaluation side. First thing, does Tiresias performance works better compared to the baseline? So we have 3 baseline methods developed. One is based on the spectral method. Then second one is on the Markov chain, which is only depend on the previous event you see. And we implemented the 3-gram. 3-gram means that it depends on the last 2 events. And the Tiresias works better, percentage-wise. We have been able to achieve on average about 8.2 precision on the evaluation side. Then we actually ask ourselves question, why it works well to predict one event out of almost 4,500 events. We did this evaluation to understand whether or not our system is confident when it reaches the right conclusion, right prediction. So from the figure on the left-hand side, you will be able to see that we are really confident when we're actually producing the right guess. But of course, if you can look at the right-hand side figure, we also try to ask ourselves the question, are we confidently wrong? The first thing that you notice at the y-axis, there are not many wrong predictions. And our confidence level is not that, when we're actually wrong, we are not that confident. So that's the first thing. The second question that we all try to answer is to see if this short-term memory actually ticking to produce a good prediction results, or this long-term memory actually contributes more. Because we can see that both Markov chain, which is 1 state back, second order Markov chain is 2 state back, they're not performing as well as Tiresias. So you can see from these figures that we show that the long-term memory has better contribution to the right prediction. And on the right-hand side, you can see the same trend that the long-term memory actually produce less wrong predictions. And there will be another 2 questions. Can we actually make sure that this Tiresias is stable enough? We train the model on different setup. We train the model either on a daily basis. So you can see the first 5 lines. We train the model based on 1-day data. And the last line is trained using 1-week data. So we will see that the more data you see, the Tiresias is going to be reasonably better in most of the cases. That's one of the things we will talk about in the next slide, is that what if we want to reuse the model we trained since we think it is stable enough? We actually have 2 different setups. First, we have reused all the models we trained in November in different settings, like 1 day and 1 week. And we re-evaluate the model performance in January and retrain these 3 models and comparing the performance. So you can see that the model trained for 1 week data in November actually has similar performance comparing to the model retrained in January in different setup back in February. So our conclusion is that the Tiresias is reasonably stable and can be reused. And I will spend a couple minutes on the limitation and probably promote some discussions here. So for the first thing, we talk about the data limitation. So that like almost all these machine learning models, Tiresias has to be trained and tuned per data set. So that would be the most important thing. You have to test by your data set to evaluate the performance. And for the prediction events, we want to be open as well, is that the recurrent neural network, broadly speaking, personally, is a statistical model. It may not be able to correctly predict the rare intrusion attempts if these are rare events, because the system didn't see enough samples before it can actually do the correct prediction. And our reviewers talk about the evasion. So the evasion is possible on the condition that the adversary has to produce a very large scale force attack. So for example, we use 740K machines to train as a sample machines. So basically the attacker has to change all its scripts, produce force attacks at a massive scale, and hope it will be picked up by the system, and then switch back to the real attacks. So that is the things, it's financially not ideal to the adversarial parties. And nothing that we think about that is the feasible deploy of the system into mobile devices, because we test our model trend per day is only 31 megabytes, and it's reasonably stable. You can actually push to your mobile devices and see if it actually produce better results. We haven't tried it yet, but it opens the possibilities. And I will conclude my presentation here. It's almost on time. Is that the prediction of security events is a complex problem. You have to understand the data set and the system you deal with, so you can actually come up the right model for the right data set. And Tiresias seems to be a good fit for this IPSP and the user behavior data set. It will be able to offer reasonable, good predictions, and our evaluation proves that it can be reused and reasonably stable. Thanks for your time. Questions?
Yeah. Any questions?
Thank you for the talk. So prediction has been there for a long time. So my question is, you can apply time series analysis. This is inline prediction, right? This is online prediction or online prediction or offline prediction?
The thing is, we have to train the model offline.
Correct, but
and then predict online.
Online. So you can use time series analysis. You can use some other machine learning techniques. What's new in this technique and how it can be an advantage over the existing techniques?
Oh, time series application. I mean, time series prediction is more about regression. Our prediction, time series is basically a regression problem. You have to predict a real value for your prediction, and our system is actually a multi-class classification. You can see that prediction is we predict a discrete class labels. Per label will be per event. So that's two different problems, I would say. So you predict the exact event instead of a value. So that's the difference.
Did you get a sense for the ground truth of what sequences it is that it's actually predicting? Is it the scan patterns of off-the-shelf script kiddie attack kits, or did you just focus on the prediction aspect?
Oh, to answer your question, I mean, the ground truth we have, basically we set up the model to predict what will be the upcoming event. So our ground truth will be from the sequence itself, what we see at the time and what we predict for the next timestamp. So our ground truth is already there in the sequence.
Sure. But did you actually look into what it is, outside of the world of, ML feature extraction? In the real world, what is it that it's learning?
Yeah, I mean, we actually have a case study in the paper. This actually we show here in the slides is actually a multiple step attack against a web services server. So they will actually try the different things based on whatever information they're connected. You can actually see that they try different ways, and then probably everything is actually script. So once you see that all the things being blocked, they'll actually try the CVE regardless.
Fair enough.
Hi, I just wanted to ask if you can explain a little more how did you choose dataset D1 and D2 and why did you choose them that way? I mean, and how did you use them in the evaluation?
Why do we choose your
I
question?
don't know, because you said like D1 is continuous and D2 was some separate dates.
Okay. So for choosing let me go back to the site so we can actually see the dataset. I can explain a bit more.
Yeah.
To choosing the dataset for the D1, we use D1 to do two things. First, to evaluate if Tiresias perform better than the baseline methods.
Mm-hmm.
That's what D1 does. A second thing that we will train the model on daily basis and a weekly basis to see if there is a performance difference between the model trained on a daily basis and the model trained using 1 week data. So that's D1's purpose. And for the D2, we randomly selected the dates because we don't want to use the consecutive dates because there could be overlap between the attacks. So this is unfair to the evaluation. We want to be as transparent as possible. So we select the different days randomly and test whether the model will be able to perform better. Or let's say we try to answer a couple questions. Whether the model trained in November can still be reused in January and February. So that would be 2-3 months gap.
Mm-hmm.
And the second question is that if the model trained in January is indeed better because they see the latest data. So that's why we choose these two different data sets.
Okay, thanks.
Okay, any more questions? I think we still have time for one more question. So let me ask you a simple question. So do you think the time between events is helpful?
That's a great question, I have to say. Taking the time into the consideration probably gonna be useful, but we haven't tested it out because the time between different security events may indicate something or may not because they may introduce the noise as well.
Right, because I'm asking because I think some previous work using Markov chain, they can consider the time between events. So maybe you want to compare with those methods too. Yeah.
Markov chain, I mean, depends on how they calculate the transition matrix. They may factor the time into the computation, but I wonder for sure if that is a practical thing to do. I mean, normally they just calculate the co-occurrence,
Okay.
so they can generate the probability.
Okay, sure. Yeah, let's thank the speaker again.